distance. What is action at a distance? Well, action at a distance is what the name suggests. They're saying that I can influence you somehow without anything between us, okay? And yeah, I can influence you somehow without anything between us in the sense that I can throw a stone at you and hurt you in your head, right? And but I'm using an object. There is something between us. There's a rock, right, that is flying. And it is an action at a distance in the sense that, I'm throwing this thing and it's flying through the air in a given amount of time and it reaches your head and you get your good old bump there, right? That we can all understand. The problem is when you get to things that happen faster than the speed of light. And now we have problems with special relativity, which says that speed of light is the swiftest thing imaginable or allowed by the Father Universe. And we agree with that. We say that the maximum speed is the speed of light. And it is because of what I just mentioned, the fact that the rope, you have the wave equation, little c, 300,000 kilometers per second is equal to frequency times wavelength, meaning number of links times length, okay? So the more links you have, the smaller the links are, and vice versa. The longer the links, the fewer links that you can have for a given length of rope. Okay, so the wave equation, C equals frequency times wavelength, can only be simulated by a rope. There's no other object can simulate that equation. So that gives us good feeling that we're on the right track as far as, the hypothesis that we propose, the rope hypothesis. Okay, so what's the issue? The issue is that no one has defined what an object is. So not only do we have a problem with the fact that these people say, nothing can travel faster than the speed of light, but you have things like entanglement that happen, what they say is instantaneously, right? You move something here and then suddenly on the other side you have motion instantaneous in the opposite direction. So for example, if here you have clockwise, over there you're going to have counterclockwise. And again, a rope explains that quite easily, right? I always like to do my little clockwise, counterclockwise. Let's see if I can do this right. I guess it's that way. Okay. And if you look, your end of the rope is twirling clockwise, right? And mine is going counterclockwise. And if I turn it around, mine is going counterclockwise, and now your side of the rope, there it is going counterclockwise, okay? So that's the issue. The issue is that it's instantaneous. Why? Because a rope can only twirl one way or the other. So even if they're on opposite sides of the universe, the two ends, it doesn't really matter. Over there, it's going to be clockwise. Over here, if you look at it from the other side, it's going to be counterclockwise, and vice versa. So that explains why it's instantaneous, because a rope can only move one way or the other way. What I mean by this is that all these experiments on that they've done, like Alain Aspect's EPR experiment, Einstein-Podolsky-Rosen, which is an entanglement experiment, they have to be redone, reconceptualized under the rope model. You cannot use particles to explain entanglement. And that's the problem, because they're saying, well, what, did the particle travel faster than light to reach the other guy to force him to turn in the other direction? That violates special relativity, and so they're stuck. They're saying, well, it is so, but we don't know why it is so. So they don't have a cause, they don't have a mechanism to explain why entanglement works. They say, let's just use it for technology. And with that, we prove quantum. Now, you haven't proven it because you don't have a theory for it. You don't have an explanation for it. What you're saying is, it is so, and we're going to use it for technology. That's got nothing to do with how entanglement is carried out. And even before that, we have something even worse, which is gravity. Gravity, we've known since man got a little use of reason, that, things fall to the floor for some magical reason. They never fall to the sky. And so they never figured it out. And they said, there's nothing there. Why does it always fall to the floor? And so what they did over the years is invent, angels and spirits and gods and so on to explain some of these things. That's how these deities came into being, because they could not explain the invisible, intangible mechanisms of Mother Nature. Okay, so we have here the definition, and this is where the problem starts, because they have the wrong, or Not wrong. It's irrational. An irrational definition of the word object, of what a thing is. So when you say, is there a thing? Is there a medium? Is there a body, substance, whatever word you want to use there, between two particles? You have two particles, one on one side of the universe, the other one on the other side of the universe. And you have entanglement. This one affects that one instantaneously. Or you have gravity. You drop something and it already is pulling on it. And you say, I don't see anything in between these two objects. Isn't there an object there? Is there a medium, an agent of some kind? And they can't see or touch one. And that's their notion of what an object is. So there's nothing there. That's their conclusion. That it just happens by magic, right? And so here they have object, a collection of matter. That's the one from Wikipedia, okay? And obviously it's an irrational definition. And you say, why is it an irrational, Bill? Well, it's an irrational definition because matter is a bunch of objects. That's what matter is. So let's replace the word matter with bunch of objects. A collection of a bunch of objects. That's what an object is. What did we learn? An object is a bunch of objects. That's why it's an irrational definition. Okay, you can't use the bunch of objects definition to define object, which is what matter is. And says an object is material inside the boundary of an object. Yeah, absolutely not, because all you're saying is that what it's made out of, which is mereology, another nonsense invented by the so-called philosophers, right? In quantum mechanics, an object is a particle or collection of particles. Yeah, so a particle is a bunch of particles. That's what they're saying. That's all they said an object is. And an object is known by the application of the senses, meaning see and touch primarily. You can include hearing and smelling, but primarily what these people are saying, if you can see it or touch it, it's an object. And if you can't, it ain't. So is air, which is a bunch of matter, collection of matter, a bunch of atoms, is air an object? And a lot of people will say, no, air is not an object. It's a gas, whatever gas is, right? And it turns out air is an object. It does have shape. Okay, and around the Earth it's like a shell. And if you put it in a balloon and pop the balloon in outer space, you'll see some kind of blob. If you could color code it, and that'll show you that air is an object made out of atoms. Hopefully, anything made out of atoms is an object, is a thing. Okay. Instead, they said that field and energy and mass are things. They move a mass, they transfer energy, they wave the field or wave the wave, And so, no, those are not objects. And that's where the problem is. Then dictionary.com says anything that is visible or tangible. Again, irrational definition. Isn't an object before you can see or touch it? I mean, before you can see the chair, right? Or touch the chair or bump into it, right? Is the chair an object? And hopefully a chair is an object always. Here in the land of the Klingons, it's always an object. And people don't understand that. They say, no, I got to see and touch it. So they rely on these senses. And they also have other definitions for object, and they have nothing to do with physics. One is a thing, person, or matter to which thought or action is directed. That's where the problem starts, because you're treating it as a subject of a sentence, as the noun or whatever. And this is where the problem starts. These people are using notions of ordinary speech, and they're bringing them into science, into physics. That's where the problem starts. Okay, so here we have one of our starting points for where they how they began with this action at a distance. You had these deities and angels and spirits that they created in the past, our forefathers. They were so intelligent, And you have the Holy Spirit, a divine force, whatever a divine force is. What is a spirit? The incorporeal part of humans. The soul regarded as separate from the body. And what is soul? The spiritual part of a living being. What's an angel? A spiritual, without a physical body or heavenly supernatural being. Okay? And so you can see all these people in the past, they had to invent all these notions of a body that has no body, a thing that is not a thing, okay, that does not have shape. And that's where the problem started, because they said, I can't see it, but there's an influence from something out there that I can't see or touch. And so they invented the spirits, the angels, the ghosts. They had to invent these things because they couldn't see what was there. And the mathematicians today picked up on all that, and they made an even worse mess. They said, look, it's not an incorporeal corpus, a body, right? What it is, all these concepts which they turned into physical objects, field, mass, time, they bend time, gravity, so on. They converted all these concepts into objects. Why? Because they never defined the word object. No one in the last 10,000 years defined the word object in a scientific manner. That's one, but even more fundamental than that, no one ever discovered in physics how important it was to define the word object. You can't do a physical interpretation without a physical object. Okay? You have to have a physical object if you're going to give a physical interpretation. They never realized that, so they never defined the word object. They went along with the notion of ordinary speech, which was done by so-called philosophers who had no stake in the definition of the word object. And so here we are today. Nobody knows what an object is, which is my greatest contribution to science, the word object. What's my word object? Here it is, okay? Something, that which has shape. What is nothing? That which doesn't have shape. See how easy it was? And you say, Bill, it took 10,000 years to come up with this? Yeah, I don't know why, but it did. And something and nothing are antonyms. That means we can use something and nothing scientifically now, rationally, consistently. Okay? We can use them because now we have solid definitions for these two words, something and nothing. We have another word for nothing. We call it space or vacuum. We also have another word for object, for something, which is object or thing, or body or whatever. Okay, so what do we have? If we're going to look at gravity, for example, which is one action at a distance, according to Mr. Newton and his successors, right? We have this action at a distance. We want to try to find out what it is, and we start with a specification. What it is that we're trying to show? What are we trying to figure out about gravity? Okay, we're trying to figure out what the mechanism is. That's what it is. And if you say it's action at a distance, means you're not putting anything between the two objects that are being attracted to each other. Okay, so here we have, I've shown this in the past, but this is a good starting point. This is a professor at Berkeley, and he's going to tell us what we need to figure out about gravity. What causes gravity, or what the specification is that you need to work on if you want to solve the riddle of gravity. Here it is. Listen to him. Okay.
If you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling on atoms right now on the other side of the Earth. There's a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay, so that's the specification for gravity. That's what we have to explain with a mechanism. We get the cause. What causes gravity? There it is. Every atom on Earth is pulling on every atom of you. Let's repeat that just in case it didn't sink in. Every atom on Earth is pulling on every atom of you. You are also pulling on it. Okay? How do you pull if you don't have a mediator, a physical mediator? What are you going to pull with? A field? Are you going to pull with mass? Are you going to pull with energy? Or with a wave? With time? Hopefully you put a physical object between two atoms. And if the atoms are far apart, you would think that between two atoms got to be something elongated. Very thin, because atoms are, very small, right? You can't even see an atom like a hydrogen atom, right? So it's got to be very thin and elongated. You're getting the specification, you're getting the idea here. It's got to be thin, and it's got to be long, okay? We got that? Because that's the only way you can explain gravity according to what Mr. Richard Muller just said, okay? But here we have these people introduce the word field. I showed this the other day as well, but we got to put these guys in there because this guy's going to try to explain gravity. How? With the word field. And field is not an object, but the funny thing is how he does it. He's going to try to turn the field into a particle, Okay, his name is Arvin Ash. He's a professor at one of these universities. And what he's going to say is you get this field, whatever field is, they showed us a bunch of lines. We don't know what he's showing for the word field because field officially is just a bunch of numbers, right? And so he's going to shape this field, and in a given region of this ocean that he calls field, undefined ocean, nebulous ocean that he has not defined, he's going to create a particle, which is not a particle because it's not a discrete particle. It's a peninsula that protrudes out of the field. Okay, keep that in mind. It's not going to be an independent particle that comes out of the field and floats around. No, it's going to be a peninsula that, like a bump in the field. So it's a peninsula. And somehow he says, well, then we have this graviton. Who knows where that came? He put it in there by hand, right? And this graviton goes back and forth and this particle causes attraction. And again, it's inconceivable because nobody can even imagine me throwing a stone at you and attracting you. You know, if I throw a stone at you, it's probably going to push you outwards, not bring you inwards, okay? So here it is. Listen to Arvin Ash. Here it goes. Listen to him carefully.
One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
Yeah, and that's wrong too. I mean, in the case of electromagnetism, you have positive and negative. In the case of gravity, there is no positive and negative. So it's not analogous to electromagnetism. But you can see he's throwing a little particle that comes out of nowhere. He puts it in there by hand. He doesn't justify where he got it. And he says the graviton is really a bump in the field. So how does he end up with a particle separate from the bump in the field, which is a peninsula? So again, it's all inconceivable what they're talking about. And of course, when you look up the word field, no matter where you look it up, and I challenge anyone to look it up, here it is, okay? Field, physics, I think the first one is from the dictionary, and the second one is from the Wikipedia, the darker ones. So in physics, the influence, that's what it is. Field is an influence, whatever that is, of some agent, whatever agent, we don't know. Yeah, the influence of some agent. And what's, according to the Wikipedia, says a physical quantity. A physical quantity. I don't know what a physical quantity is. A quantity, I know what it is. Like the number 5 is a quantity, like 5 apples. You know, that's a quantity of apples, 5 apples. But a physical quantity, I have no idea what a physical one is. Never seen one. Physical means it has shape. So I don't know any quantity that has shape. And then down at the bottom, you see a field according to math, okay? A number system, according to dictionary.com. And in Wikipedia, it says a set on which addition, subtraction, etc. are defined. So what is a field? We have no idea. Certainly it doesn't belong in physics, the word field. And so these people have turned these numbers, these values, these quantities, amounts, and they've turned them into physical objects. And then you start vibrating them and say, oh, it's the field that's vibrating. You can't do that in physics. You have to identify the object if you're going to give a physical interpretation. And if you're not going to give a physical interpretation because, as mathematicians say, it's not part of their job description, then they should keep their mouths shut. They have no way, they have no priority over you, more intelligence than you, or any authority over you in telling you anything about how this universe works if their line of work has nothing to do with physical interpretations. If they consider that as philosophy, they should keep their mouths shut. Instead, they go out there and say, oh, we know all this stuff. Oh, you know it? Yeah, because the math tells us all this. And so they infer their ridiculous theories, their explanations. When you call their bluff, they say, well, it's not in our line of work anyways. You're talking about philosophy. What we do is math. Then why don't you stick to math? Stick to math, do your math. I don't care, describe quantitatively, and just keep it there. Keep it within your field of work. Don't come into physics and tell me how this universe works, and when I call your bluff, you say, well, we don't do that anyways. They keep on and on with this. if their job is not to interpret how this universe works, then they should not even attempt to do it, okay? Because they have no superiority over you in that respect. You have as much right as any mathematician to tell them or the world how this universe works. They should not have a monopoly over that line of work, okay? Okay, so how do we destroy all this stuff with the universal movie, okay? You cannot say that field, which is right there at the bottom, you can see it there. Field requires at least 2 frames of the movie, right? Because field is a bunch of numbers. And especially when they vibrate them, they're using up to at least 2 frames of the universal movie. Every single frame in the universal movie just contains every atom in the universe. Okay, they're all static. You've taken a snapshot. You got God's camera. You took a snapshot of the universe. It's a 3D frame there, a 3D picture. And you've got every atom where it stayed, like you froze the universe. And then in the next frame, every atom in the universe moved to a new location, and so on down the line. So every frame represents the location of every atom in the universe. Father Universe only exists in the present. He doesn't live in 2 frames. Okay, so every atom in the universe is in a single frame of the movie. Okay, so you can't use the word field because field is a dynamic concept, especially when they vibrate it to create a particle. Okay, so that was Arvin Ash's version, the quantum version of what they're trying to do with the graviton, right? They say this particle and how it attracts. The analogy is like electromagnetism, positive attracts negative, right? We don't know why that's so either, but here we have the official version, right? And I'm going to have Brian Greene. He's another so-called mathematical physicist who's going to try to tell us how it really works, what gravity is according to general relativity. So here goes. Listen to him.
The ball travels along an indentation in the fabric that the heavier object creates. And this, Einstein realized, is how gravity actually works. It's the warping of space-time caused by the objects within it. In other words, gravity is the shape of space-time itself. The moon is kept in orbit not because it's pulled to the Earth by some mysterious force, but rather because it rolls along a curve in the space-time fabric that the Earth creates.
Okay, so that's the official version. Warping of space-time, gravity is geometry. That's the official version. But for that, what did good old Brian Greene have to do? He had to turn space into a physical object because you cannot bend a concept. And so they said, no, space is a physical object. And so this is how he justifies that. He had to do this. He had to turn space into a thing. Otherwise, you would have this action at a distance, right? With nothing in between. And he said, no, there is something between. It's called space. And space is a physical object. That's the thing that is between the 2 objects that are attracting each other. So here's how he converts space into a thing. Okay, listen to him.
As she spins, she feels her arms pulled outward. But now let's imagine that you could take away all the stuff around her. So the only thing left is the skater spinning in completely empty space. If the skater still feels her arms pulled outward, she'll know she's spinning. But if empty space is nothing, what is she spinning in relation to? Trying to answer questions like these, scientists came up with a bold new picture of space. And the key was to make something out of nothing. Space is real. Even though you can't see it or smell it or touch it, space is enough of a real physical thing to provide a benchmark for certain kinds of motion. Like that skater. Newton would say that when she spins, her arms splay out because she is spinning with respect to something. And that something is space itself.
So now you know how the mathematicians converted nothing into something. They did a magic trick. They turned nothing into something. They turned vacuum into atoms. They turned space or nothing, any of those, into physical things. And so that was their solution. They had to do that because otherwise they would have action at a distance, right? At least in general relativity, which is the bending of space, time, right? And that's for gravity. That's how they fix gravity. But obviously they cannot reconcile that with the graviton, with quantum mechanics. So we have two worlds. We have the world of the graviton, which is the one for quantum mechanics, and we have the world of general relativity, which is the one that's got to do with the background, not with the particles themselves like the graviton. It's got to do with the background, the stage on which all phenomena take place. Okay, and so this is where the problem is. The problem is that they cannot reconcile one with the other, and they look for the theory of everything. They're looking for what is known as string theory, a way of uniting, general relativity with quantum mechanics, and people reject that as not even being physics, not even wrong, as they say. It's not even rational. That's what it is. And then we have another phenomenon, which is this weird one, which is entanglement, which I talked about a little bit today. And here we have someone, his name is Matt O'Dowd, and he's going to tell us a little bit about that. He's going to try to show us how that's done, again, without any mediator, and it's done instantaneously. From one end of the universe to the other, it's done instantaneously, and let's see what kind of object he proposes to have that done. What's in between these two particles, one that can affect the other one instantaneously, in violation of special relativity, by the way. How does he do it? Well, let's start slowly. Let's let him give his little presentation here. Listen to him first here.
The Nobel Prize in Physics is typically awarded to scientists who make sense of nature, those whose discoveries render the universe more comprehensible. But the 2022 Nobel has been awarded to 3 physicists who revealed that the universe is even stranger than we thought.
I like that. He says they gave the Nobel Prize to these 3 so-called physicists because the Nobel Prize is given to people who clarify how this universe works. And it turns out these people clarified nothing. They got the prize anyways. They got their $1 million anyways. Great. Just give prizes out. I think those Nobel Prizes are worth a dime a dozen. You can get anything at the 5 and 10 cent store, right? Okay, so he continues. And he's going to tell us a little bit about the fact that Albert Einstein, good old Einstein, that he was wrong about entanglement. Entanglement really does happen, which was known as EPR until then, Einstein-Podolsky-Rosen experiment, EPR. And Einstein said, it's spooky action at a distance. And so all the quantum mechanics proved Einstein wrong. And that was one of the problems that Einstein really had. So here goes. This is what Matt has to say about good old Einstein and action at a distance, entanglement.
Experiments that proved that the strangest prediction of quantum mechanics is actually true. It's the prediction that Einstein refused to accept. The idea that 2 quantum systems can be entangled, bound to each other, such that they can influence each other instantaneously over any distance. This spooky action at a distance, as Einstein called it, is in seeming violation of his own theory of relativity, which tells us that no causal influence can travel faster than light.
Okay, so we have the spooky action at a distance, and I guess he's going to tell us how it works, because, if they're going to prove Einstein wrong, right, and say, hey, you were wrong, Einstein, okay, fine, then means that they have a solution, that they know how it happens, because then they can prove Einstein wrong. Otherwise, they're just saying it is so, that it happens, but they don't know how it's happening. They don't know if it's instantaneous or not. They say it is instantaneous, but you can only say it's instantaneous if you know the mechanism. If you don't know the mechanism, you cannot say it's instantaneous. And again, I like to point out that with my rope, right, this is instantaneous. When this one goes counterclockwise, yours have better go clockwise. simultaneously. And if it goes the other way, it's instantaneous again. And so this is not instantaneous in the sense of particle traveling from one end of the universe to the other. Okay, so the word instantaneous has to be qualified here because it depends on what you simulate the physical interpretation with. Okay, so here goes man. He gives us an introduction. He says if you put you have a white ball and a black ball, right? You put them in two boxes while you close your eyes, right? And so you don't know which one is black and which one is white. You close the box, right, while you're still, with your eyes closed, and you take one of them to the moon. Okay, so you take one to the moon. All you have to do is open your box, and if it's a white ball, the one on the moon is a black ball, and vice versa, right? So you don't have to travel to the moon to find out. So you don't have what he calls information traveling. I don't know how information travels, but that's how these mathematicians talk. They say you don't have to have information traveling faster than the speed of light to understand that if you have the white ball here, the other guy's got to have the black ball on the moon. Okay, so listen to him. This is more or less what he says. That's a starting point for, to explain entanglement.
You have two balls, one black, one white. You close your eyes, shuffle the balls, and place each in an identical box. You put the first box in a rocket and send it to the moon, while you keep the second box with you on Earth. While that box is closed, the ball on the moon has a 50-50 chance of being black or white. You open your box and you instantly learn the color of the ball on the moon. So, did you cause information to travel faster than light? Of course not. The information about the ball's colors was always there with the balls. You just learned which was which.
Okay? One fellow there asks, but how can it switch from clockwise to counterclockwise instantaneously? I thought I answered that question. Let me answer it again. I usually don't answer in real time, but since I saw the question there, I'm going to answer it. And that is that the rope only twirls in one direction. Okay? Twirls in one direction. No one can measure one rope. No one can measure one rope. We cannot measure an atom because it's so small, and the rope is thinner, gazillions of times thinner than an atom. So if you take a hydrogen atom, right? Let's assume this is the hydrogen atom, and let's assume this is the rope that's merging in it, right? That rope there, this thing that you see there, this thread that's going in there, is gazillions of times thinner than the ball. Okay, so here is not a good representation. It just gives you a ballpark idea of what I'm trying to say. That's all. But other than that, this thread is much, much, much thinner than the atom in Mother Nature's universe. So let's start there. So we cannot measure a single rope. Okay. Now, what do? They go in there and they put polarizers and analyzers. I don't know if you're familiar with ellipsometers, okay? But they put a polarizer and an analyzer. They send a beam, and what they do is they just measure at a cross-section of the beam. But a beam is made out of gazillions of atoms. Gazillions of atoms. So they don't know if it's a single rope there is twirling clockwise or counterclockwise. They really don't know that. And then they say when they force the light to switch in the other direction, like now we're going to force the atoms over the ropes over here to switch counterclockwise. It's instantaneously clockwise on the other end. They don't know if they force them to twirl in the opposite direction because you cannot measure a single rope. The whole experiment has to be re-evaluated under the rope model. These people are talking about particles, and they're thinking of a ball like this, and then it's twirling. That's what they think is happening. So they have a cross-section right there. They say, oh, we're measuring a single photon, right? And this one is going, clockwise, for example, right? And the other one's all automatically going counterclockwise. So here, from this side, it's clockwise. From this side, it's counterclockwise, right? And then they say they force it to go in the opposite direction. They cannot know that for a single rope. And so, again, this experiment has to be looked at under the rope model. It's got to be reevaluated completely. And that's all I can tell you. Okay. It's not that they force a single rope to suddenly twirl in the opposite direction. And this fellow, I guess, is thinking that we're doing this, right? That if the rope is twirling in this direction, right? Suddenly we force it to go in the opposite direction. That's what he's thinking. And so he says, well, if it's going in this direction, right? And suddenly, I force it to go in the opposite direction, that signal now has to go from one end to the other and slowly force it to turn around. That's what he's thinking. He's saying, look, it's moving in this direction. We now force it to move in the opposite direction. That signal, that propagation, right, has to now travel, right, from one end to the other. And he says, how can you do that in a rope that extends throughout the universe? And the answer is, it doesn't happen. It doesn't happen in nature. We need to reevaluate the EPR or entanglement under the rope model and find out what we're really doing, what we're really measuring, right? And I doubt that they're going to reach much conclusion because there's no way you can measure a single rope. So exactly what they're doing over there when they put their polarizers and analyzers, I have no idea. I don't think they know what they're doing either. They just measure and they say, oh, it's going clockwise, counterclockwise, and when you turn it around, it's the opposite, or clockwise versus counterclockwise, and so on. So it needs to be re-evaluated under the rope model. That's my answer to that. Anyways, let's continue here. Matt now is going to prove to us that it really, entanglement happens faster than the speed of light. Okay, that's his conclusion. And again, because he hasn't modeled it under the rope model, right? He hasn't simulated it under a rope model. So this is what he's going to say. Listen to him.
Imagine that these are quantum balls with entangled quantum colors. According to quantum mechanics, we not only don't know which is which until the box is open, but the colors of the balls are fundamentally undefined. Each ball is in a superposition state of maybe black, maybe white, until a measurement is made. Opening your box causes the observed ball to have to choose a color state, which then forces the ball on the moon to choose the opposite. Now you really do seem to have an effect that travels faster than light, with the ball on the moon switching from a superposition state to a defined state as soon as you make your observation.
So with particles, it's even worse because you don't have a mediator. Okay, so the ball has to travel, or something has to travel from one ball to the other, from, the information has to travel, as they say, right? Okay, so we have all these concepts traveling around the universe, all this information. And the question is, if you instantly change the black ball to a white ball on the moon, the one on the Earth immediately changes to the opposite color. Explain that one. I challenge you. There's no way you can even imagine it. That's total magic. It's nothing but black magic what they're talking about there. They don't have a mechanism. That's the point. And if they don't have a mechanism, they cannot say that that's exactly what happens. Okay, that's why I'm saying the experiment has to be reevaluated under the rope model and find out what we're actually measuring, what we're actually doing in the labs, right? I don't think they've got a clue as of this moment. And again, I've used ellipsometers where we measured, primarily refractive index and so on, on glass, which is what they use in the industry, in the semiconductor industry. And yeah, it's a great tool for certain things. And the question is, again, can you use that tool to measure a single rope? And the answer is no, absolutely not. There's no way you can measure a single rope. Okay, it's just too thin for what you're trying to measure. You can measure an atom and say the atom is twirling in one direction or another. That I think you can do. That doesn't mean that you can measure the rope that comes out of the atom, because it's just too thin to be able to measure. You can't measure a rope. It can't be touched. So much less can you measure it. So what I think they're measuring is atoms. Okay, they're checking the atom, which way the atom is spinning, and the atom can spin this way. It doesn't mean the rope coming out of it is going to spin in the same direction. Okay, so anyways, let's continue here. Here we have good old Brian Greene. He tells us how how gravity actually works. Okay, listen to him carefully. He's going to tell you, okay, this is not me. Okay, he's going to tell you how gravity works. Okay, and he's going to confirm Newton's theory. Here goes.
How does gravity actually work? How does the Earth pull on the moon across hundreds of thousands of miles of empty space? They behave as if they're connected by some kind of invisible rope.
They behave as if they're connected by some kind of invisible rope. They behave as if they're connected by some kind of invisible rope.
But everyone knew that wasn't true. And Newton's laws provided no explanation.
Okay, so we have the answer. The answer is the rope. The moon is attached, but he was wrong. It's not one rope, it's many ropes. Every atom on the moon is connected to every atom on Earth, even to your body, every atom in your body. So now we can explain physically what's happening. We can say, okay, why doesn't the moon fly away? Well, it doesn't fly away because it's attached, physically attached to the Earth. Now we can understand it. But if people say, there's entanglement, there's gravity, action at a distance, what have we learned? All we're saying, there's a ghost, there's an angel, there's a deity, a god, right? That's working magic between the Earth and the moon. That's all we're saying. Again, action at a distance is what in the old days they used to call witchcraft or black magic. That's what it is, real black magic, not just a magician doing a trick on stage, right? Here's a rope model, that we have for the black and white balls that Matt talked about. In a single frame of the Universal movie, the ball is either black, one ball is either black or white, and the other ball is either white or black. Okay, so you cannot, in a single frame, they have a given color. They have a certain wavelength or length. Okay, in the next frame, right? I don't know if they can change from black to white and white to black in a second, in a split, in just a single frame difference. Okay, they can change locations, but can they change colors? Well, I guess they would have to go from one frequency to another instantaneously, which I'm not sure that's possible. But even if we concede that, it doesn't matter. The argument here is that within a single frame of the Universal movie, the black ball is going to be black and the white ball is going to be white. It's not like, we won't know if the cat is dead or alive until we open the box. No, the cat is either dead or alive according to Father Universe. Whether you know it or not, that's something else. And what these people are saying, that the wave function collapses of the cat, right? And so suddenly when you open the box, he turns into one or the other. He's either alive or he's dead. No, not true. Father Universe doesn't work that way. The cat is either dead or alive before you open the box. Hopefully, Father Universe does not do miracles, does not work by magic. But these people have concluded that Father Nature works by magic, but they don't call it magic. They call it things like, action at a distance, And so under the rope model, very easily, we show how the astronaut falls to Earth, right? Because every atom in his body is attached to every atom on Earth. It's physically attached. The ropes are not concepts. They're physical objects that we cannot see or touch. Okay, the definition of object is not that which you can see or touch, but that which has shape. And hopefully you can see for yourself that each of those lines that I drew there have shape. Okay, so the ropes have shape. Many of them attach to your body according to Professor Miller, and shows why why you have acceleration of gravity towards as an astronaut falls to Earth. It also shows why gravity goes through things. Why? Because it goes right through the atom, because the rope goes through one atom, it doesn't touch it, right? And it goes to another atom behind it, behind it, behind it, behind it, all the way to infinity, right? In other words, if you have a line, if the astronaut was at infinity, somewhere way far away, all the ropes that connect them to the Earth superimpose. Gravity is very weak, right? Because It's pulling like with a single rope, the whole thing. It's a single coaxial. And only when he approaches the Earth do the ropes fan out. Now you can see why there's an acceleration of gravity the closer he gets to Earth. Okay, so now we have a physical mechanism that we can all understand, we can all visualize, we can all illustrate. Okay, we can make a movie of it. And otherwise, what these people are saying, this thing that they call action at a distance for gravity, for entanglement, for all these things like the gluon serving between quarks inside the atom and inside the neutron, well, we call it witchcraft and black magic. Okay, so coming up at the end of this month, we have witchcraft and black magic. I guess the day of the mathematical physics, that's what they should call Halloween. They'll rename it, So trick or treat.